If people don't like know hypothesis testing, they tend to like this, or the reverse. It's like the people who want things to be black and white, line in the sand, don't like this. And the people who are like, I'm sick of these rules, like this. I don't know. Anyway, so getting into the real actual analysis part, I've kind of structured this into 3 parts. So the first question you have to answer is how many factors or components should I run? Okay, so we're going to test for how many factors there should be. And then we're going to test if I can achieve simple structure. I'll explain that a little bit. And then after you get the simple structure, is the solution adequate? So you could have a simple structure that is a bad solution. And so it's sort of like I could have an ANOVA that runs, but it isn't significant. It's kind of the same idea. And this is just sort of the way I've structured it. People talk about these 3 things with those terms, but not necessarily as like step 1, step 2, step 3. So how do I figure out how many factors there are? And people will talk about this as extraction. It sounds so like medically. Right? So how many factors do you want to extract from the data? Or pull out, essentially. I would think about it as running. How many factors should I run? So for criterion, the first one's theory. Do I have one for each one? Yeah. Okay. So theory is I've designed the scale to have 3 factors. I would expect the scale to have 2 because the previous people who designed it said it has 2. And so this is sort of like previous research / if you're doing scale development completely from the bottom up, how many you would have expected. So I have a funny story about my friend's scale. What is it called now? The FQQ? I don't remember. It's changed names 3 times. That she wanted to be fight, flight, and freeze. So measuring their fight or flight response and like how often people sort of freeze up. I swear we ran that thing 5 stupid times before we finally got that 3rd factor. It's finally gotten published too. Woo! But it took quite a lot of time. So theory, it was going to be 3. It's going to be 3, and I'm like, nope, still 2, still 2, still 2, 4, nope, 2, and finally we got 3 out of it. So even though I have a theory, it doesn't always work out that way. Right? But that's a good place to start. What's called the Kaiser Criterion, the same as the Kaiser statistic. Okay. This is not as popular anymore because of reasons we'll get to in a second, but people still talk about it, so make sure you know what it is. The old rule was to take the number of eigenvalues, I'll explain eigenvalues in a minute, over 1. So if I had 6 eigenvalues over 1, I'd go for 6. The new rule is the number of eigenvalues over 0.7. I do not know where those numbers came from. It's in there. It's magic. So it's called the Kaiser Criterion, but there is an old rule and a new rule. So what the heck are eigenvalues? So we talked about how factor analysis takes a correlation matrix and says these are correlated and smushes them together. Okay, eigenvalues are a representation of that smush. So it's how much variance is accounted for by grouping these items in this way. So it's a lot of matrix algebra is what it is, but it's a number that represents how much variance for this factor and this factor and this factor. The confusing part is on the output. What you'll see is if I have 23 questions, I will get 23 factors. So it takes all of the variance and says, here's a big group of variance, make that factor 1. Here's another group, factor 2, factor 3. And it does it until it's out of variance. And so that means it'll use all 23 questions to make 23 factors. Okay. Only a couple of them will be big. So you're looking for the ones that are large. This isn't a super popular rule anymore because it doesn't always match the rest of the statistics we'll do. The other theory, the Scree plot, and parallel analysis. But I am going to have you run it just so you know how to do it. Okay. So eigenvalues are just a way to say this much variance is accounted for by this factor. The other thing you can do with eigenvalues is to create a Scree plot. This is super popular. You pretty much have to say that you did this. So a Scree plot, now these were made in SPSS, the other Scree plots look a little different, but it calculates the number of factors on the bottom, so this would have had 20 questions on it, and then it plots the eigenvalue on the side. So I got 6. First, the eigenvalue is very large, and then they sort of taper off. So in this one, what we're looking for is a really big drop. And so at this point, they level off. Right? So there's only one above the part where they sort of flatten out. And in this one, there's two above where they flatten out. Looking at these sometimes takes a little bit of like looking at a bunch of them. But you're really looking for what's called the point of inflection. That's not on this slide, it's in a couple slides. The spot where they just sort of all start being about the same. So we're looking for a large drop. The cool thing is the psych package in R will draw the point of inflection on there for you. Woohoo! The other thing we're going to do with eigenvalues is a parallel analysis. So what it does is it takes the eigenvalues of the data, then it takes the data and randomizes it, and recalculates the eigenvalues again. And so a randomized data set should not have very good eigenvalues because it's random. And so you're looking for the number of eigenvalues that are significantly larger than a randomized data set. So it kind of matches that null hypothesis idea where we don't expect anything to be related. So it scrambles your data, not a meta data set, your data, and says, here's what a random data set would have, here's your data set, these three are bigger than chance. So use those three. Okay. So you want them to be bigger for your data than randomized data. And it also makes it very clear because it says parallel analysis indicates 3 factors. Okay. So there's no guesswork there. So what do you do if they don't agree, which they won't, because life. Okay. We won't do this on the homework because then it would make the homework very long, but in real life you test several different models. So if your theory said 3, but your parallel analysis said 4, you would do 3 and 4 and compare them and look and see which one was a better fit. In general, simpler solutions are better, so less factors. Okay. And that's the what is it? That law that has a name. Occam's razor? Right? Simplest solution is the best. We don't call it anything fancy except parsimony. So simpler solutions are better. The problem is that simpler solutions don't tend to fit better. When we get to adequate solutions, we'll talk about why. All right, so let's try it. So this, I think, do I have theory written down? No. Okay. I can't really remember what the field book said it was supposed to be theory. It's either 2 or 3. Okay, so we would have an idea on theory. I would think 3. Math, the math questions, the R computer questions, and then the statistics only questions. That's kind of what I would think. But you'll see that this is going to be an interesting mix of numbers here in a second. Okay. So what we're going to do is fa.parallel. That is in the psych package. So that will run a parallel analysis. For the life of me, I can never spell parallel. I want it to be AL. Okay. So what you do is the name of the data set. FM is ML. So FM is factor math, would be my guess. ML is maximum likelihood. Okay. A lot of this is wait 3 more slides and I'll explain it a little better. But we're going to do maximum likelihood for reasons we'll get to in a minute. And then FA, factor analysis type, is factor analysis. So if you wrote PCA there, it would do principal components. If you did both, it would give you both. And we're going to stick with just factor analysis. So I'm going to save it so I can look at stuff. And then I got my EFA data, ML, and FA. So this is the only thing you got to change is the name of the data set. When you run it, it will automatically give you a couple of things. But the first thing we're going to do is this note factors fa.values. That's the eigenvalues. Okay, so run that. Okay. So did I cut and paste them? No. Anyway, okay. So down here I've got all of my eigenvalues. You'll notice that some of them are negative, which means that they're not variance, I guess. I don't know, these are supposed to be variance, but they can be negative. So the first one takes up 6 points of the variance. Now don't think about this as a percent. That's not the way it works. Okay, this is not scaled. This is a variance. So it's not proportions or anything. Okay. The next one down is almost 1. And I got 6 for So you can tell that the big drop on the Scree plot is because it goes from 6 to 1, right? Which is what this is showing. But to make things simpler for the Kaiser Criterion, the next 2 lines down I have is tell me how many of them are over 1. That's the old criterion. Tell me how many of them are over 0.7. So it could be like really obvious. So if you can't count, this will do the counting for you. So I'm going to sum up the ones over 1. So there's only 1, which is clear, right? 6. Sum up over the ones over 0.7, and that's 2. So right now we have it as 1 factor or 2 factors. So we already don't agree. Then I said 3 a minute ago. So we got 3 different numbers. And so that will let me total up for the Kaiser criterion. But I've already said that isn't the best idea. So let's look at this, the Scree plot. So it gives me the graph of them. And so what you'll see is we're looking for the biggest drop. So I would say 1. And that's what this line is here, telling me the big drop thing. But it also will show me the dotted lines here. It shows you both dotted lines at once. The reason you can't see 2 is they're on top of each other. And that will give me the point of inflection. So it levels out here. So it could be 1 if I do the big drop, or 5 for the point of inflection. So that's why there's 2 different lines. So 1 if you do the big drop idea, 5, so 1, 2, 3, 4, 5 for the point of inflection. So we have now 1, 2, 3, and 5. That's why I love factor analysis. Half the time it's kind of like I get to make it up. All right, is everybody see what's going on with the graph? Yes. And then just in case it wasn't clear that we needed another number, it says here parallel analysis suggests 7. So the number of factors is 7, and then it says the number of components is NA because I did not tell it to run PCA. So you can actually run both at the same time. So 7, so 1 twice, 2, 5, or 7, 3 if you add 3. So in a real paper, I would run each of those and say which one was the best. But I'm not, because that you guys would kill me. So we're just going to do 2. And so that whole thing up to here is how many factors should I run. So we're going to pick 2, just for simplicity's sake, and see what happens. All right, so the next thing down, the fitting estimation, or the factor math part, is what kind of math is used. So everything we've done this year has been least squares. We've talked a lot about least squares. That's the good variance over bad variance stuff. Now this is a different type of math. And there are a couple of types. I'm going to mostly tell you to go with maximum likelihood because that's what everybody does. But it depends. So I'll show you some of the other ones. If you're going to do EFA, maximum likelihood, there's a star because that's like not seen any other version of that in a really long time. So what maximum likelihood is it takes the data that you have and sort of iterates and finds the most probable outcome. Okay? So it's the data point with the maximum likelihood of being the right point. You'll see that in most EFA and structural equation modeling. It's really popular. The math is very stable. It tends to run. That's why people like it. Alpha factoring is another option. I don't remember how it works. It's a thing. Principal axis factoring is actually somewhere between EFA and PCA. Depends on who you talk to, which side they put it on. Image factoring is for PCA, and then principal components factoring is PCA for principal components analysis. So we're going to stick with maximum likelihood. All right. Now rotation. This is like my least favorite part. It's going to be some interpretive dance. All right, so we figured out we're going to do 2 factors, mostly because that's easier to draw on the board. And let's say we have data where they clump together oh no, don't do that. Here. So if I were to plot the points of all these different data points for each person, these would be our questions. Okay. What we'd start with is a solution that requires it to be at 90-degree angles. Okay. So this is regression line 1, and this is regression 2. Okay. This factor analysis is regression on steroids. Okay. And so if I picked 2 factors, I would get 2 regressions. If I pick 3 factors, 3 regressions. So we're going with 2 because I can draw that on the board. What rotation does is it allows me to get to simple structure. So simple structure is like making it simple and easy to interpret. And there are rules for it we'll get to in a second. But I can take this preset y equals x, or y equals the average score, and rotate it. That is not any different than saying the null model in a linear model is y equals the mean. Okay. And then adding the x variables. And so creating a slope with these variables, and so rotating it from flat to not flat. We talked about that last week. How regression tests if the addition of this variable or all of the variables is better than the average. So with factor analysis, we start with the average. It's a little more complicated than that, same idea. And we're going to rotate it to get a better solution, just like you would rotate regression.
Could you draw what the axis labels would be? I'm just trying to follow the graph. I'm a little lost. So like what's the y-axis and the x-axis?
The factors themselves, yeah.
So it's factors and the scores
Per
person? So is each dot one
It's
participant?
not quite that simple, but this would be factor 1. Factor 2. How do I explain it? These would be like the loadings they would get, each item would get for that factor.
Oh, okay.
It's not eigenvalues, it's the like
The actual
weight
later. Okay.
that you would get. So it would be B, basically.
Okay.
Something like that. So I probably shouldn't draw this, right? Because it's not quite y and x anymore.
Okay.
Alright. So rotation helps us achieve simple structure by increasing communality. So remember, communality is how much the items correlate with their or R squared for them. And what that does is it maximizes the loading of items on one factor and minimizes them on other factor. So it takes that question and says, you go there, and you're not part of this. So it's basically creating these groups. There's 2 types, orthogonal and oblique. And you will not do an orthogonal, or my statistics instructor will murder you. But I'll tell you what it is. So orthogonal rotations are here on the left, and they force factors to be uncorrelated. So we're going to say that this factor and this factor are totally uncorrelated things, and so it forces the regressions to rotate at 90 degrees. So that's why it's still straight lines here. Well, we've already predicted this set of dots pretty well. So if I force it to rotate at 90 degrees to get these other dots, I don't have another color, do I? Oh, yeah. So an orthogonal rotation, I would get these dots pretty well, but I would not get those dots pretty well. So any combination of a 90-degree rotation, the interpretive dance part, only catches one set of dots. And that's because we're assuming factors are uncorrelated. How often in psychology is anything uncorrelated? Like never, right? And you put them on the same scale because you expect them to be related things. So there's a popular scale, the DAS, depression, anxiety, and stress scale. And to say those things are uncorrelated would be a joke, right? So instead, most people do oblique, which is the right side, which allows factors to be correlated. So it doesn't force the regressions to rotate at 90. Now what I can do is keep this one here and rotate this one. So get rid of this line real quick. So now that's allowing them to be correlated. It's not 90 degrees anymore. This picture's better. I'll take it from the book. So an orthogonal rotation forces them to be uncorrelated and rotates at 90 degrees, which makes it uncorrelated. A oblique rotation allows them to be correlated. So the reason nobody does orthogonal in psych is because that's just not a thing. We expect things to be correlated. Otherwise, why are they on the same scale? And so you get a much better interpretation of the data with an oblique rotation usually. Okay? It easily works better. And so that's kind of a sum of this. So it assumes they're uncorrelated and rotates at 90 degrees. That means the variance between factors is completely separated, which is kind of how ANOVA works. Remember we talked about it's model variance or it's error variance. It's like it's factor 1 variance or it's factor 2 variance and nothing in the middle. A couple of types, varimax, quartermax, and equal max. I wish I could tell you that the word max is a good way to know that it's orthogonal, but that's not true. Because promax isn't. Duh. Varimax is probably the most popular orthogonal one. Don't do it. No, bad. Instead, do oblique, which allows them to be correlated at any correlation. So they can be super correlated or not correlated at all. So it allows them to overlap. And this big star right here. So I like to ask this question too. If your factors are truly uncorrelated, the oblique rotation gives you the orthogonal rotation because that's the best fit. So why, that's my little question down here, why would we ever do an orthogonal rotation? We usually believe they're correlated, and if they aren't, they happen to, this case, not be correlated, you get the same results. So I don't know why anybody does orthogonal. I think because mathematically it used to be easier to do by hand. Just my best guess. But with computers, meh. So don't do orthogonal, always do oblique. The most popular one is direct Abelman. SPSS does normalize direct Abelman, so if you do this in R and SPSS, you will get slightly different answers because it does a slightly different form of direct Abelman. They're usually not very different, but not perfect match. Promax is another one. And we're going to do direct Abelman. And at least it kind of matches like Abelman, oblique, they kind of start with the same letters, if you remember. So we're going to do maximum likelihood because the math tends to run. And so the thing about the math, this table, people like maximum likelihood because it gives you the least number of problems. So sometimes your it'll run and it'll just be like, bleh, and it won't give you any answer. And there are lots of different options to try in the psych package. There's unweighted least squares, graded least squares. Am I remembering that correctly? Ordinary least squares is like 800 least squares options. That would also be EFA style. And it will usually recommend, like, this didn't run. You want to try this other thing? It's easy to switch it out. Okay. Which is why I need to test the test to make sure it runs first. Okay. All right, where am I? So with simple structure, so we're going to use maximum likelihood in a factor analysis and do oblique rotation. What do I get? So the output's going to include the loadings. These are not eigenvalues. These are the loadings. It's the correlation between that individual item and the factor. It's also going to show you communality and uniqueness and something called the complexity index. And what I want is items to load over 0.3. That seems like an arbitrary criterion until you remember that the R equals 0.3 is a median effect size. Bless you. So we want at least 10% of the variance. So we're going for at least a medium loading. 0.3 is usually everybody's kind of lower criterion. If it doesn't load at 0.3, we can get rid of it. Or if it double loads. So it loads on both factor 1 and factor 2. You can go higher. I have done analyses where we were trying to get rid of questions to make a short form, so we went with like 0.6. But you can't really go lower. So you can't say, oh, I'm going to do 0.2. People will be like, really, why? And so it's called simple structure because we want each item to load on one and only one. Even though we're going to let factors be correlated, we don't want items to cross-load, or what's called double loading, cross-loading, same thing. Because that makes interpretation more difficult. So this is trying to get back to parsimony. We want questions that measure this factor only or that factor only, and not the other factors. So it is a little weird that we allow the factors to be correlated, but then make sure the questions do their own thing. And there are times when people let them double load, but you got to have a really good reason. I saw somebody suggest that once in a review, and I was like, that's unusual. And then the next person in the next review was like, why'd you let them cross-load? And we're like, oh, we can't win. No winning here. So double loadings are considered bad, and no loading, like if it doesn't load at all on none of the factors. That would be bad too. And so what you'll do, sorry, before I go to the next slide, is you'll look at the loadings in the output and say, this question's bad and this question's bad. You'll eliminate it and run it again. This one's bad, take it out, and run it again. So you might run this 3 or 4 times before you get down to the questions that work and are stable. Okay, so the point is we're trying to get to a simple solution. The other thing you have to consider is that if you have a factor that only has 2 items, 1 or 2 items, that's called a unique factor, and you actually should eliminate the factor. So if you had 4 factors and only 2 items loaded on it, try running 3 instead. And that is when you're going to get rid of factors. Usually you're getting rid of questions. Sometimes you get rid of factors. What I've had happen to me before is it started with 4 and it was going fine. So we started eliminating questions that double loaded. And by the time I got rid of those, factor 4 only had 2 questions. So we got rid of factor 4 and tried again with only 3. And it worked much better. Okay. So let's try that. Oh, so here's that summary. You might run several rounds, take out the bad items, run it again. Generally, people don't allow cross-loadings or double loadings. Sorry, people use that term interchangeably. Generally, don't do it. Right. Let's try to run it now. So when all items have loaded adequately, that's the term people use. You can use it when you're writing up your results section. So they've all loaded adequately. So 1 and only 1. So the code for it is FA for factor analysis. Also confusing. That could also be PCA. But data set name, no in factors. So we're going to do 2. We could do 3. So that makes it really easy to switch out the number you're going to run. Rotate equals Abelman. Okay, so that's the rotation type we're going to use. Math maximal method. So let's do that. Right. So it's kind of scary how easy this is because there used to be a disaster to run in this program that we were using. And now it's just 1 line of code. It's kind of nice. Okay. It gives you so much output. Oh my god. Okay. So when you run it, you're going to get all this output. What we're going to do first is look at this table. So the standardized loading table is called a pattern matrix. And it actually cut and paste nicely, which is unusual, right from our... so we've got this pattern matrix. And so here's commonality, that's H2. Uniqueness, it's U2. And complexity. So complexity is a measure of how much it's loading on multiple factors. So we're going to look at each item individually. So M1 just means factor 1. And the order that they go in is by how much variance is accounted for. So you might run a round and then the next round they might flip. That's not a big deal. So we're going to look for the loadings to be over 0.3. You want high commonality and low uniqueness and low complexity. Okay? Simple structure, so low complex. I haven't ever seen a good cutoff score for complexity, so it's just they kind of give it to you, but we're not really going to use it. So for this first one, it's okay because it's only loading on the first one. Does everybody see what I'm saying? Yes, stop me if you get lost in this part. If you're good with Excel, you can dump these into Excel and have it highlight it for you. It's really pretty. The second one is okay. Negatives are alright because it's only loading on the first one. Third one's okay. Fourth one, yada yada yada. I think it's 23 that's bad. 9 is iffy, but it's below 0.3 on that second one. 11 is on factor 2. Right. So you would just look through all of them. I recommend cutting and pasting it into some other program just so it's easier to read. 23. Okay, so when I get down to 23, it doesn't load on anything. Okay. So it's not above 0.3 on either one. So we're going to get rid of that item. That's what this fancy table is. So we're going to remove 23 because it doesn't load on either, and remove them again, and run it again, sorry. So that's why on here it just says minus 23. So I'm on line 41. So if I look at this one, this time they're all going to load adequately or load cleanly. That's what people say sometimes. Because, like I said, made up data. Real data sets are going to be messier. So everything loads cleanly on one and only one. So if achieved simple structure. Questions on that. You might run it 4 or 5 times. And then it might blow up on you. You never know. Nice, quiet. All right. So the last question you have to answer is adequate solution. So I came up with this simple structure. Is that structure any good? This is kind of like p-values. We're not going to have a p-value this entire time except for Bartlett's test. But this is sort of a different way to think about fit and how good is it. It's going to be a little backwards from p. Okay. So we're going to talk about fit indices, reliability. Most people are familiar with Cronbach's alpha, I hope, and then theory. So fit indices, oh, I forgot I took out the definitions of these. Okay. So the original matrix is the original correlation table. Okay, so we created that correlation table, that's it. A rotated matrix is the correlation table that's after it's been rotated with Eigenvalues, okay, or whatever one you pick. So we have a rotated matrix and an original matrix. Sometimes the rotated matrix is called the reproduced matrix, because heaven forbid we have one term for all these things. And what it does is it takes the solution that you got and the original data set and overlaps them. And it's a measure of how well those two things overlap. So kind of think of it as like, here's what we started with, here's what we ended with, and we want them to match. So if our factors are truly a good representation of the data, they will match the original correlation table. We want them to match. So this is really weird. We want the null to be true. Ugh, that kills people when I teach sim, because I spent all year being like, false, false, false. Most descriptive analyses, you want it to be true, which is a hard sell. So there's 2 types, goodness of fit statistics and residual statistics. So goodness of fit statistics get their name by they're the good ones, so we want them to be large. So it takes that reproduced correlation matrix, the real correlation matrix, and correlates them together. So it's the correlation of the correlations. So you want it to be highly correlated. I know. So it takes your data, the data that the model that you came up with, and overlaps them. And you want it to be big. So I give you some rules. They're the same for all of them, but it's a pretty table. A couple different types. The non-normed fit index and the Tucker-Lewis index, they're the same stupid math. But depending on whose research lab you've come from, you might call it one thing or another. So they're the same. The Tucker-Lewis index will be in the output we're going to look at. The comparative fit index, we're going to calculate because you can't get one of these published without CFI anymore. And then the normed fit index, not to be confused with the non-normed fit index, is another one that you'll see. There's also the goodness of fit index and the adjusted goodness of fit index. I have them right here. Don't use them. Bad math. Bad. So they'll always tell you your model is good, which is why people like them, because your model's always good, but they're not well supported anymore. And there's about 12 more of these. Every day there's a new fit statistic born into life, which is the joke of sim. So there's incremental fit index, the starts with an R. There's a bunch. These are probably the most popular. The residual statistics, so the reverse. It takes our reproduced are our new correlation matrix from the model, the rotated one. Takes the real correlation matrix and subtracts them. So these will be the residuals. We've dealt with that word before. This is the error. So you want the error to be really low. So RIMC is the most popular. Root mean square error of approximation. You have to have it. Okay? People question your sanity if you don't have your RIMC. You want it below 0.06. That is not 0.05. It's 0.06. Just for fun. Okay. 0.06 to 0.08 is acceptable. Don't ask me what happens when you get 0.9. Because these are the standards from several different books. But above 0.10 is poor. So most people say 0.06 to 0.9 is acceptable. And then the RMSR. So it's the root mean square of the residual, not to be confused with the SRMR. So RMSR, root mean square. SRMR, standardized root mean residual. They're not quite the same, but it'll give us both of those very easily. So we're getting the error. Basically, we're getting the good variance estimate, the bad variance estimate. It's kind of what's going on. And we want the good one to be big and the bad one to be small. Because heaven forbid we all do the same thing. So this is in the output. You will look at this at the last model only. I don't think that's in here, so be sure you add that. Okay, so this is only on the last model. So if you can never get a model to get to simple structure, you would never do this step. You would just kind of start over. So in our example, the root mean square residual, it's even got the little cute little abbreviation. It's 0.05. Cool. Okay, that's good. It gives us the RIMC, 0.07. That's in the adequate range. And the confidence interval that you want to include. It's always 90%. 95 for everything, right? 0.05, 0.05. RIMC is 90%. That's all I got for you. Okay, so people use 90%. The BIC on here is the Bayesian Information Criterion. Just lovingly called the BIC. There's another one that's AIC, which is named after a different dude. Those are really popular for comparing models. So models with lower BICs and AICs are better than a comparative model, another model of the same type. We're not going to do a whole lot of model comparison, so just ignore it. Okay. They don't have cutoff criteria. So the TLI is bad. So here's Tucker-Lewis right here. It's 0.84, so that's in the not acceptable range. So what about the CFI? I'll be damned if it doesn't give it to you. So where am I looking for this in the output? I'm going to scroll past the proportion of variance accounted for. It gives you the factor correlations. So our two factors are correlated at 0.6, which is kind of high. And that gives you a whole bunch of crap. But here's RMR. Okay, more crap. Here's the other two indices. So what about CFI? It's not a thing. So I'll give you the formula. It's not terrible. Okay, so chi-square model divided by, minus degrees of freedom model divided by chi-square null minus degrees of freedom null. I don't know why they don't calculate it because all of that is in the output here. But I can never, the wording here is just super awkward, the objective function. So what I just did was made it calculate myself. So whatever you want to do for final model, save it as final model. So we're going to save it instead of just viewing it. So whatever this last line is here should be here. And then this is the math for that. So statistic and DOF are the model chi-squares. Null chi-square and null DOF are the null chi-squares, obviously. So it's 1 minus, sorry, I left that out here. It's 1 minus this thing. You do not have to know that formula. I was just showing you where line 45 came from. So you would run that. You will know that if you have done it moderately okay if it's slightly larger than the TLI. It should not be exponentially larger or smaller. If you get 0.45 and your TLI is 0.8, you've done something wrong. And honestly, you won't have to change this formula as long as you call this step final model. So our CFI is 0.87, that's still not really acceptable. So what do you do if half your fit indices are good and half of them are not? I don't know. You try and publish it and you see what happens. You see what reviewer you get. Depending on what reviewers you get, it might get published or might not. Meh. So that, I don't know. So people tend to, the problem that people have with this and SIM is people will often cherry pick their fit indices for whichever ones they like the best. And so that's why I say you pretty much can't get it published without RIMC and CFI, because those are the two that we've all agreed on that, like, if one of them's going to be bad, that will help answer if you've cherry picked the rest. So people like those a lot because they're very familiar, and you can tell if people have sort of only shown you the ones that were significant. Also, you can tell what program they used, because different programs will give you different ones automatically. So SPSS gives you this many. None. 0. So bonus for not using SPSS. It will run these analyses, but it gives you the chi-square and just says do the math yourself. The program that I used to use that's free but is cranky at best will give you all of them, but this is like a good middle of the road solution. Okay, it's pretty easy to run. All right, where am I? Okay, so we did this. And then the last two pieces, reliability and theory. Okay, so we're going to try and see if we can get this published, because we got half good, half bad. Let's see what the reliabilities look like. So reliability is an estimate of how well your questions hang together. So it's kind of a measure of how your items get along. So if people answer 7 on this one, do they also answer 7 on this one? You've already told me they're really correlated, so they should. Chromebox alpha is the most common. I don't know that people know that there are other ones. Do you guys know there are other ones? There's lots of them. It's kind of insane. There are other ones, but Chromebox is easy. 0.7 or 0.8 is acceptable, depending on who you talk to. You could also do split half reliability. So you take the data, split in half, do Chromebox in this one, Chromebox in that one, and see what happens. We're just going to do regular reliability. Whoa, this slide. This is clearly a book slide. So Klein, who's a structural equation modeling dude, said it should be over 0.7. But here's the tricky part, and this is also true for the factor analysis itself. Factors with more items will fit better. Models with more factors will fit better, because you're allowing for more of the data to be accounted for. But that does not mean that a 4-factor model is better than a 2-factor model. It just will fit better automatically because it's got more factors. So one of the tricky parts about factor analysis is if you have a 2-factor model and a 4-factor model, the 4-factor one will have better fit statistics, but you have to tell if it's that much better. Is it worth having all 4 factors, or should you go with 2? And that's more of the theory part. Okay. So if they fit exactly the same, people say go with parsimony with a simpler model. Or it should be 2 factors. One important part here, big highlights, treat subscale separately. So don't run Chromebox alpha on the entire data set unless it's all 1 factor. And be sure your reverse score items are, remember to reverse score reverse place. Terrible sentence. Make sure they're reversed. Because generally correlations between items are positive. That one would be negative because it's reversed, and that freaks out alpha. And at this point, we've already done that. Code is very easy. Alpha. Data set. So something I don't think I've taught you guys this year, kind of a cheat that you may like or you may hate. So what I did was I created myself a vector, so factor 1, factor 2, that has all of the column numbers. So where did I get that from? What you do is you look at the final output. Every time I say that, I want to be like, final countdown. Mostly because it's the last day of real class, right? So I take my final output here. So question 1 goes with item 1, because that's where it's loading. Okay. Question 2 goes with item 1. Okay, so I picked those out based on which one they had the higher loading on. So 1 through 7 are all factor 1. 8 is factor 2. 9 and 10, factor 1. You get the idea. So I just made myself a list of those in vector format. So 23 isn't in there at all because we dropped it. What you could do is just do this C thing here. Well, I don't know, it made it clear for me. The other way this would be nice is if you are wanting to do subtotal scores. Okay. So I made myself just a list of all of where the questions went. And so you can tell we only have 3 items on factor 2. So it's pushing the edge of like how many items we should have. If you run those, since it's just a list of numbers, you can use that to say which items you want. So I can run my reliability statistics saying just give me factor 1 or just give me factor 2. So one of the biggest mistakes people make on the test anyway is they just run all of them together. Just say alpha and they give me 1 number. I'm like, there's 3 factors, there should be 3 numbers. So as many as there are factors. All right. It gives you some crankiness because some of them are negatively correlated with each other, which you can see by looking at the output. So that one's negative. But it mostly, the thing you want to look for is at the top. So raw alpha is Chromebox alpha. Right? It gives you a whole bunch of crap. Then it gives you the confidence interval for alpha 2, which is nice. So that confidence interval is really small, which is good, right? Small confidence intervals are good because we have 2,500 people. But then if your alpha is bad, so let's say you got, oh, what did I do? I must have shown you factor 2 on there because I got 0.77. Can you just get 0.77? Yes, okay, good. We're not going to have another ANOVA moment. Oh, that's weird. That does say factor 1. No ideas. Anyway, 0.77, which is okay. But if your alpha was bad and you want to see like which question is the problem, then this piece here is just the reliability if you drop that question. So sometimes you'll see reliabilities go up a whole bunch because there's one bad apple. And then I would go back and look at it in factor analysis. Usually they agree. But all of these are hovering around the same. So if you have one of these that was 0.2 and the rest of them were 0.8, 0.9, that would be the bad question. I would consider dropping it. It also gives you the item statistics, which is kind of nice. Gives you the mean and the standard deviation out here on the side for each item. And then the frequency of responses for each item. And this just shows you how many people, proportion, pick 1, pick 2, pick 3, pick 4. And that's interesting if you're wanting to see like if people never pick 1, will never pick 0, that sort of thing. It'll show you like how often people pick each end. But generally what I do is I look at alpha, and if alpha is okay, like the rest of it, And if alpha is not okay, I look here at reliability if item is dropped to see which one is the problem. Or are they all bad? Sometimes they're all bad. So reliability for factor 1 is okay. Reliability for factor 2 is 0.82, so it's also okay. So our model fit statistics are like half and half. Our reliability is okay. What about theory? Almost done. So theory is where you look at the loadings and you look at the questions and can you label them? So this like comes full circle. I expected 3 factors, but we did 2. Do they match what I was expecting? So one problem we had with this fear, flight, and freeze study was that the freeze and fight, I think, can't totally remember, items kept loading together. I'm like, why are these going together? This one's like, I stood here like a log, and this one is, I punched the guy. Like, why are they loading together? I couldn't figure that out. So sometimes the loadings don't line up together, and that would be bad. Or you'd have to come up with a good reason why these 2 items would go together. And they're negatively correlated, so that's why. So do the loadings make any sense? Can I label them? So I would take this structure, so 1 through 7, and now I'm going to look at the scale. So we know that 1 through 7 are all on the same factor. And then it actually would be easier to do it the other way. So 8, I can't remember, 11 and 17. 11, 17. Oh, whatever. You get the idea. So I've never been good at math. I did bad at math in school, and I slip into coma when I see an equation. Those are clearly math-related items. So the second factor is a math question. If I look at all the rest of them, so every other item, it's mostly statistics and computers, right, and R. So computers, central tendency statistics, R, eigenvectors, R eigenvalues, distributions, and this one didn't load at all, so it doesn't count. So clearly the first one is the R computer statistics part, and the second one is the math related questions. So at least that makes sense. So you're trying to label what they would be. So the last piece is the theory piece. So on this one, I would probably try to get it published, even though the fit indices are half and half, because the reliabilities were okay and this part makes sense. And I would say it's a exploratory analysis where other people should replicate it and show that it still works. And then move on with my life. Only other thing I have included in here is an example of overfactoring. On this you can just kind of run individually. But what happens is, let's say we did 5 factors, because that's one of the other suggestions was 5. And 5 factors, I can't really do 7. I can kind of do 7 because I have 23 items, but 5 would make more sense. So at least 4 on each one. But if you start with 5 factors, what happens is you slowly get rid of questions one at a time, and then your last factor only has 2 items. See if you get rid of that. And then as you're getting rid of more and more questions, then this factor only has 2 items, and it ends up being a 2-item scale, but you only have 8 questions left by the time you're done. And that is a good indicator of overfactoring. It's too many factors. So if you have a set of loadings where you're slowly eliminating factors because the questions have all fallen off, try a smaller number of factors first. So you'll see that people call that overfactoring of too many factors. Underfactoring is the other way, where you run 1 and you say, look, good enough, there's only 1, and people go like, well, if you look at these questions, really it should be 2. So if I look at the way the items load, it probably really should be 3, because the statistics and computers ones really should be separate things. So say this is probably slightly underfactored. There are so many questions on item 1 that I might try 3 and see if I can get them to separate out. All right, so that is factor analysis.